recording. That looks crazy, kind of. Hello. Okay. Yeah. So just like when I start erasing, please say don't erase. Right. So let's try to explain. So basically, this last week we were doing kind of more exploratory kind of like what else is out there. Can you get like a little bit of a handle on this more, I guess, novel and more sophisticated usages of crypto? And we went with the zero knowledge last last lecture, and let's try to do explain, to the best extent we can in this format what multi-party computation, so multi-party secure computation computation is. Acronym is, comes from these letters. Okay. So actually, this was a picture in the first class. It's like one of these beautiful things that cryptography can do. And the picture was that you had a bunch of parties. And each of them, and there is some algorithm that they want to perform together. Think for this that this algorithm is a deterministic one, so it's basically a function. So a function taken inputs that are submitted by n parties. Think that they have some inputs that they would naturally submit to the computation. So think, for example, that these are different hospitals. They have databases of their patients. They have some health algorithms that they can perform on their own database. For example, correlate like that. Do they have an outbreak of some disease? Well, if they have only 2 cases per week, it's not an outbreak. But if they have like 10 cases with some sort of then that's an outbreak. Now, think that instead there's a bunch of health institutions, and they can like they would like to perform this same computation on like the joint data. So there is some function that outputs. That is actually, without loss of generality, vector of outputs. That there's this magic function. I mean, not magic function, that's interesting. And the function and it computes outputs. So it says y1 to this, y2 to this, etc. If we have trusted authority, like a trusted person who is saying, okay, some sort of health association that says, okay, each hospital gives me all your data, I'm going to compute this function, I'm going to give you the output. Okay, then it is. Is there a cryptographic protocol which allows them, which has the same functionality? But no trusted party. Okay, so what could they do? In other words, could they instead engage in some protocol? Can P1 run some protocol on his inputs that determine, he's sending messages perhaps to all the other participants, and P2 also sends messages based on this stuff, right? Such that at the end, each of them has their outputs. And so it is for all the other participants, right? What does there exist? This mysterious protocol that would have, well, the following two properties. So first of all, after they're done, they do have the same output that trusted third party. This entity is often referred to as trusted third party. Why third? Because of GGP. Because you and I try to compute something. Let's say that there's only 2 hospitals, not n. And we kind of have a quandary. Like I have my patient's data, you have your patient's data. If I send you my patient's data, you could compute this, but I would violate secrecy of my patient's data, and vice versa for you. Well, if there was a trusted third party, some sort of a sworn person who says, I'm not going to leak anything to anyone, I'm going to compute this correctly for you, and I'll immediately forget all the answers. Then we will give it to this person and he would compute it for us, right? But obviously, in a normal world, it's just pushing the buck, right? Like, somebody you have to trust, right? Cryptography can give you a solution where they follow some protocol, where they emulate the functionality. So they get correct out, but it has the following security property. So the 2 properties, correctness, parties outputs are as in computation. Okay, so the protocol guarantees that what is going to compute is function f, whatever this function f is. So of course the protocol depends on function f. Somehow, without functionality, think of f as a Turing machine or a circuit, right? And whatever that circuit is, the protocol is going to do something that depends on that circuit. And because everybody knows the circuit, and these people they're aware of what the function f is. So based on f, they're going to send some messages, and they will process the messages sent by counterparties. And with knowing what f is, and they will keep on doing this, and the protocol will guarantee that the outputs of f on some exercise contributed by these n parties. But well, that by itself would be, in some sense, trivial to accomplish. We just broadcast exercise, and everybody computes f local. So, but that's obviously, just a trivial solution that does not protect anyone's privacy, right? So what is privacy? Intuitively, it's like this. For each even if all other parties are corrupt, so think of a hospital, like, this is UCI hospital. And let's say that it agrees to perform this computation with UCSD hospital, some Anaheim hospital, I don't know, some other hospital. So let's consider a situation where all the other hospitals are ganged up against the UCI hospital. And they might have two objectives. First of all, try to learn what are as much as they can about X1. Because they contribute, they're all in a gang. So there, x2, x3, x5, you know, we don't care about the privacy because we just in this scenario, they're all attackers. What is it that they learn about x1? And we want to say that they learn the minimum. And the second objective is that perhaps they can manipulate what the full UCI is going to output. Perhaps they can get UCI to think that, oh my God, there is a complete breakout of the disease. There isn't. Let's skip this. Let's assume that somehow the second requirement is part of correctness. Okay, it's actually somewhat complicated to state and to what does it mean? Because okay, here is the complication. They take what x2, x3, and so forth is. So if you really think of them as a gang who works against you, well, in the very least, what they could do is fix their inputs. So perhaps they populate x2, x3, xn with like all sorts of crazy data, so that my output, even if they submitted this crazy data to f, my output y1 would include all sorts of weird stuff, right? So intuitively think of this like this. The only thing that they can do to steer my y1 is that they have freedom in choice of x2, x3, etc. Whatever they contribute, it's f computed on that, and no other manipulation of my output. Just that. Okay, but let's focus on privacy. So even if all parties are corrupt, whatever x1 star xi minus 1 star of xi plus 1 star xn star inputs they choose. The only thing they learn about x1 is their output. Sorry. So this is consensus, probably not. Okay. Is there anybody with us there? No. Oh. So this yeah, and here. Okay. So the attacker chooses outputs of the other hospitals who are in the gang. The good hospital enters his data. The computation is F. They cannot manipulate that. These values are outputted, and the gang does learn their output. So if the function, for example, says that, if there is more than 10 people who have certain disease, I reveal exact identity of these 10 people. Then, if 9 of these people are here, and these guys guessed this 10th person with a proper disease that matches the 9 people here, then just because we agreed, this guy knows what the function is. So he knows that the function is such that, well, it will reveal everything about the 10 people, like if they have the disease that matches others, well, then that's what they compute. But nothing else, just that whatever function f that we agreed to, that P1 had to agree to compute, that output will be reviewed. In fact, the correctness property is very similar. It just says that everything is actually the same, but it just says that this missing output here, the yi, that is the one that PI computes. That they cannot view it in any other way except by picking the inputs that they want to contribute to the computation. So think of, here's an example of a secure computation that we already had. F is the password authenticated key agreement. Okay, so what is this function? It's a function like this. My input is a password. Password 1. Let's say that take the number of people who play the game is 2. P1 contributes password 1, P2 contributes password 2. And this function is actually, it's not deterministic, it's a randomized function. But you know what? I can make it deterministic if I do this. This one also picks a random value and contributes it. This one also picks a random value, contributes it. And this protocol is like this. The function has the following code. If P1 equals P2, then Y1 equals Y2 equals R1 XOR R2. In other words, I'm going to give you both an output that is an XOR between the two random values that you sent. That's a good key, because if one of them is barely awake, they're going to send a random add. And so the key that they get is a random value, which is good. They can now use it, right? And if the two passwords match, they get a random key, right? Else, Y1 is R1 and Y2 is R2. Okay, that's the function. That's the code of function F. And that's the values they compute. Okay, so think of a very, very simple circuit. If you wanted to describe it as a Boolean circuit, as digital hardware, it would have very few gates, because it takes bits of the password. It just performs XOR and then an AND to test equality of 2-bit strings. And then based on that bit that says they were equal or they were not equal, it either XORs the two other parts of the inputs and gives this as an output, or it forks and it just ping-pongs back whatever they gave you. It just replies that. Okay, this is a secure peg. If I have a protocol, if pi is an MPC, secure multi-party computation, but for 2 people, so it's like a special case for just fixed number of people for F, for this F, then pi is a secure peg. So last week, we talked about authentication, and we talked what does it mean to have a secure password authentication. And we said the secure password authentication problem is basically like this, that if this good guy picks his password at random in some dictionary, then whatever protocol I have, if this guy outputs the key, then I can output the key equal that one only with probability 1 in the size of the dictionary. Okay, this is like a simplified definition. Okay, the definition was slightly more complex. It wasn't that I only needed to compute it, I actually needed to distinguish it from a random value. But think, just simplify that an attacker, so this is an adversary, and this is a good person who runs on some passwords. So they chose at random from some, with some entropy. Let's say that we are having a guy who just picks his password from an English dictionary. It has 10,000 words, let's say. So it should be only with probability 1 in 10,000 that I authenticate to this pool too, right? Because you know, he picked a random password. So yeah, this protocol accomplishes that because whatever the gang, which is now in this case my counterparty. Okay, so this is my good guy. This is my good guy here. This is the PI. He has some inputs, so PW. And now, whatever the only things that this mechanism says, the only things they learn about my input is their output, which is if this is the attacker, then that's what they learn. Why one? Yes, because it just simplifies that there's not n people to just one. I mean 2, and 1 is good, 1 is bad. Here in this picture, P2 is good, P1 is bad. So the only things they learn is Y1. Now, what are they learning according to this? They were free to choose their input. But after that, there is nothing, you know, they're fixed. The protocol computes function F. And the code of function F was that it compared their input to the good guy's input. If they happen to choose the same one, well, game over, because they basically get a random key. They basically, by the way, they notice, because you know, if this is a long random string, then the probability that this is equal to that is the probability that R2 is 0, which is negligible, right? So they notice, but you know, basically interaction with the code, like this is like an interaction with an oracle that tells you, you guessed the password, or no, you didn't guess the password, sorry, right? And in addition, if you guess the password, then you're getting a key that you can now communicate with, because, right, because these outputs, Y2 and Y1, in this case, are secure keys. So like if this is long, right, if this and this, then this is actually a good key. But you can think of much more complicated cases, like for example, hospitals who run arbitrary computation on their data. And you can think of, here is another case that we said at some point during class that we would like to be able to compute. It's asymmetric peg, so a client-server peg. But here's another example. Where the sorted hash is distributed among servers. So the server code. So rather than store hashes of passwords of all your clients in one place, so when it's compromised, the attacker can do offline dictionary attack, distributes this. So attacker has to compromise all of them in order to get password data. Okay. So what is the computation now? The computation is there is a client. Okay. So well, let's call client P0. Okay, and then there is the servers. So this will be P1, and server arm will be PM. The client contributes his password drawing. Each of these guys contribute their share of the password hash. You know what? Let's put this in a bracket. The salt, okay? This is going to be easier to talk without the salt. And then there is some function F, which tells them some outputs, right? y0. What should these outputs be? Okay, let's just do this. Y0 is the same for everyone, so everybody just gets like a group key. Okay, like you might want instead to have pairwise keys, or just one server gets a key or whatever. But let's just say that they all get the same key if hash on password prime is equal to the XOR between all these shares of that each server stores, right? Yeah. The password hash is not sitting in one place, it's split between the servers by just one-time pad kind of splitting, right? Like I make all of them random, except of the last one. The last one is an XOR of the hash of the real password with all the others. So if you think it's like a kind of a distributed one-time pad, like everybody works as a one-time pad for everybody else. It basically has a property that, let's say all of us do it. So all of us have this, you have H1, I have H2, H3, H4, H5 to H15. Even if I took 14 of those, they are random strings that leak nothing about hash of the password. But if I take all 15 and then I XOR them, and now I know what's the hash of the password. So now I can do an offline dictionary attack, right? But only if I compromise all servers. So in practice, of course, you wouldn't do the 15 servers, but like maybe 2 or 3, I guess, right? So it's a very useful thing, and the circuit is very simple in some sense. Take one input, hash it, and compare it to XOR of our other inputs. And there is many examples where we could do it, like computing hospital stuff on large data. Maybe it's complicated, but actually, if you look at this, like very often in practice, you look at actually, maybe it's not. Maybe it's just a simple counting. Okay, like you put people in a bucket based on some disease signifier, and it's like a simple thing. Like you either have this vector switch on a bit in your data or you don't. And it's just that. And then we just count. Okay, so perhaps some of this computation is actually quite simple and it already would be useful. What are another sort of, another application is like a certification authority. It has, in a PKI scheme, it has a key that certifies all keys. If somebody got that key, then they can certify anything they want in the whole network. They could say, I'm Amazon, you are Bank of America, you are Citibank, and you create phishing websites, and you can steal everyone's data and break into, every bank account, right? So it won't be good. So these CA keys, it's good to protect them really nicely. Can they be distributed? So can a CA not, can CA signature key that is used to create certificates? Can this be split? So what's F? It's a signature computation that takes secret sharing of the signature key, performs the signature, and then vanishes. Right? Just outputs the signature and then, then they are done. Right? So every time they have to issue a signature, somebody says, okay, here is the message. It says that my public key, my identifiers, the domain name, whatever. They authenticate this person, and after they are done and say, okay, yes, we should issue the certificate, then they contribute sharing of the secret key, computed in the same way, let's say. And to XORs all these shares, performs signature. Yeah. So there's many other examples one is machine learning, right? So you have people who learn on data. Can they learn on joint data without revealing individual data pieces? Right. So this, let's say, for spam detection. So Xi is a male of me. X2 is male of you. Could the male be sitting encrypted on the servers? And nevertheless, distributed computation between us figures out learning algorithm that detects spam without each of us surrendering all our data in the plane to the mail company. Because that's a big thing. Like yes, you can have encrypted mail, except that you cannot have virus detection of it, right? Okay, let's try to see how would we accomplish such a thing. Okay, so now is a good time to photograph. Basically, what would what I want to do is to give you some examples roughly how could different approaches to this multi-party computation problem. So you get a little taste of what actually you can solve these things, and how do they roughly look like. It's a very active area. The fundamental results were given in the mid to late 80s. At the time, I think most people thought of this as kind of cute, usable, but very unlikely to be practical. And then as time progressed, more and more people looked at it, tried to improve efficiency, first just because, it's a nice algorithmic thing. And then more and more because hey, perhaps we can actually solve the real world problems using these techniques. And now we have like companies who are basically creating these systems so that to allow business. So with some recent talk I was listening Nigel Smart from Catholic University Leuven, Belgium, I guess, and he showed. So here's a problem. There's a bunch of banks, and they have transactions list, and you want to figure out like whether there's enough liquidity in the system. So when they all process the transactions, they can. Because the transactions might be like, the bank has only $1 million cash, but the transactions like that, it has to pay 2 million there, 3 million there, 5 million there. And perhaps there's other transactions that actually send the money to the bank. So in the end, the bank is fine. But he cannot start processing these transactions before knowing that it's going to be fine. And sometimes they're in deadlock. So I owe you 2 million, you owe him 2, you owe him 2, you owe him 2. None of us has to. But if we knew that there is a cycle like this, we could basically zero out these transactions and do them, on paper, right? There's tons of this kind of stuff with like financial fraud, detection, money laundering, like, these applications are endless in both finance and health and probably many more. Okay. So one MVC solution number one, it's for arithmetic circuits using secret phrasing. Okay, and so here is what do I mean by arithmetic circuits? So take prime yeah, okay, let's say prime modulus P. Assume inputs are all values in CP. Okay, so this is an integer range from 0 to p minus 1. Okay, and without much of generality, like, you know, maybe my inputs is like 1 million of these. Okay, so it's like I'm just emulating million parties, each giving x1 to x million. Yes, and then and assume f is composed of additive mod p and multiplicative mod p gates. In other words, computation looks like this. Perhaps x1 and x2 is added mod p. Everything is mod p, and perhaps x3 and that result is multiplied. So this is addition, and this is multiplication, and perhaps x4 and x3 are also multiplied. But then these results, let's say, are added. Okay, and that's the output. Let's say y1. Okay, and there is all sorts of other gates that determine y2, etc. Okay. Well, who cares about these circuits? Well, like, you know, some operations that we do are natively a bunch of arithmetic operations. So a lot of learning algorithms are actually it's matrix multiplications, finding distances, gradients, and then based on the threshold of these gradients, like somehow changing the matrix and then recomputing again. Okay. They're natively arithmetic computations, although there's additional gates that are like less or equal, yes, and it's not fully obvious how to emulate those, but so a more the arithmetic circuits can emulate Boolean circuits. So you can encode inputs, Boolean inputs into arithmetic ones. And if actually modulo 2, okay? If this is all modulo 2, then you have Boolean straight away. With small modulos, there is some problem with the technique. So actually, you need to embed somehow mod 2 operations in a larger field. But okay. These circuits, nevertheless, are first of all natively they might be interesting for some computation, and also you can actually embed general, like so. As you know, hardware and software are equivalent to some sense. So in terms of polynomial complexity, if you have a Turing machine that is efficient, and you also have a circuit that is, in some sense, roughly comparable. Yes, in practice, that's not exactly that. Like, you know, some computation definitely want to compute in a, you know, using random access memory rather than have a circuit for it. But you know, I just erased a bunch of examples where, you know, the circuit complexity was very small, and they were useful examples. Okay, so how would you do this in a multi? If your function was of that type, is described by the function, by the circuit like this. Okay, then how do you compute it? So number one, each party secret shares its input xi among all parties. Now, what is secret sharing? I'll give you an example of, we will actually use specifically the Shamir's secret sharing. It works like this. It has parameters Tn. N is the number of parties that participate in secret sharing. T is the threshold. Is the sort of adversarial threshold. Which means two things. Up to T parties learn nothing from their shares. So their shares are like one-time paths. Okay, they basically know nothing about the secret share. Secret. Any T+1 parties can reconstruct the shared secret. If you set T to be n-1, then you have the security that I was talking about before. That UCI hospital, it can secret share the data with all these other hospitals, and nevertheless, because T is equal to n-1, even n-1 of them learn nothing. But of course, all of them need to be able to reconstruct, or otherwise data is lost. So here's how Shamir secret sharing works. It has two procedures. First, there is a procedure share that is given its input. Okay, each PR secret shares its input among all parties. So I'm going to call this procedure is going to be applied to each of these. But let's now bracket the fact that it's applied to all of them, and just think of one, and call that one X. This procedure works like this. Pick a random polynomial of degree P in ZP, random polynomial F, such that f of 0 is equal to x mod p. What is the random polynomial? So x, you know what? Sorry, let me change this. I'm going to call the secret s. Because x is better to be used, I'll have notation, but x is better to use to argument of a function. So the f of x, if f is a polynomial, is a0 plus a1x plus a tx to the t mod p. So picking a random polynomial means picking t+1 coefficients. Picking them subject to this constraint simply means a0 is equal to x. Right? Because when you evaluate this function on x equals 0, all these drop out, the value of f of 0 is just a0. So it's this. So this simply means pick the free coefficient as equal to s, that each of these is random in ZP. So pick a random polynomial of degree t such that f of 0 is s means simply this, to make a0 equal to s, pick all the other coefficients at random. So that's the first step. The second step, send share Si equal f at I to player or party Pi. There's n parties in the system. Each of them is going to, each of these will be shared exactly following the same protocol. So everybody has a secret. It's going to pick a random polynomial and it's going to evaluate this polynomial on n points, 1, 2, 3, 4, n, and give evaluation at point I to party Pi. Okay? And that's it. That's the sharing protocol. There is a second protocol that is called reconstruction. That protocol takes any set of shares, any set of shares that are size for t+1 players Pi. Okay, so I want to say I can take any t+1 of these shares and I can reconstruct. So I will show you. Here is an intuition. Take t equal 1. So if t equal 1, then polynomial is a linear function, right? F of x is s secret plus a1x. If you have 1 point, so if you are one party, okay, no matter who you are, okay, you have this value here, this value. Do you learn anything about s? And I say, no, you don't. Because, you know, this could be this line, it could be this line, right? It could be this line. You, from one point, you know nothing about where you know that this polynomial, this line passes through this point, but you have no information about where does this line pass this axis, because this is you know, this is x equal to I. This is your point on which, you know, you hold the value of f at that point. The secret is the value at x0. So perhaps, you know, this is the secret if this is the line, and this is the secret if this is the line, etc. Right? You don't know which one is the case. In fact, the value of this polynomial is a random point mod p. Because for each, if you fix I, mod p, which is prime, a random choice of a1, which is random according to this procedure, means that this whole thing is random. Yes, because basically both addition and multiplication are a random shift, random permutation in the group ZP. Mod p, these are they shift you into random points. But if you have 2 points, so there are two players, right? So we have to argue two things. T parties and nothing. And this is just a simple example of t equal 1. But t plus 1 can reconstruct. Well, t plus 1 is 2. And once you have 2 points, you can interpolate. And you can interpolate the polynomial and find the side. Right? And this works for higher degrees. So for every degree, if you have t minus 1 points of a t-degree polynomial, modulo prime, these are randomly distributed. It's like random t values, independent of the free coefficient, because random, you basically these are t random points, and because it's a linear operation, you can think of like how the matrix looks like. It's all like a one big one-time pad. You getting a completely random t values, the result of this matrix computation, independent of the x. But once you have t plus 1, then you can reconstruct the polynomial. So this is polynomial reconstruction. Polynomial is called polynomial interpolation. Reconstructs the whole f, and therefore f of s, which is f of 0. Right? So by reconstructing, interpolating a polynomial means that given the values, I get all the coefficients. And then I just have to read off the first one. Okay. So okay, so this is the first. This is the procedure that we have used. We'll be using this computation. We'll be using. Okay, and the first step was that we have secret shared, and so each player secret shares its input, and then works at all. But and then for each gate, glass or non-board, compute secret sharing of, for each gate, let's call it G. Okay, G of the two inputs, X. Okay, unfortunately, this is done. Of Z, which is equal to gate from secret sharings of X, and from secret sharing of X, and secret sharing of Y. So, in other words, I don't have this input. So a normal person would get all the inputs and would compute the set, right? Now we don't. We have secret sharing of all these inputs. They're secret shared. That's what happened in the first step. Okay. And now I haven't told you how, but this is going to be our objective. From given secret sharings for any gate we choose, starting bottom up, we have the whole group has a secret sharing of x1, meaning I have some share of x1, a value, a polynomial value, output of a polynomial that was chosen by the guy who contributes x1. And you have another value of this polynomial, and so do everybody. At a different index. Let's say my index is 1, Jonathan's index is 2, your index is 3, etc. And likewise, we have a sharing of x2. So I have a polynomial value of some other polynomial, the secret shares x2. And so do you, and so do you. Each of us has this on their index. Is there some protocol that would allow us to use these two secret sharings to compute secret sharing of this wire, call it W1, the first wire out? If we knew how to do it for every gate, arithmetic gate, then we would process by recursion, right? Now we do it for another gate. And let's say this wire called W2. So is there a protocol that would allow us, having secret sharing of X3 and secret sharing of X4, to create a secret sharing of a product of X3 times X4 multiplied T? Because that's the product that should sit here. And if there is such a protocol, then we just apply it again and again until, so this wire is called W3. We would run the same sub-protocol used here. We would run it here, but now in reference to these two secret sharings to create secret sharing of that wire. And finally, we would use the same protocol we used here, but now in reference to these secret sharings to create secret sharing of the final output. The last part is, of course, this. How to reconstruct the final output. Right? So if the final state is that we have the secret sharing of all the outputs, then now we just run a reconstruction procedure for all of them, except that Y1 is supposed to be given to me. So all of you are going to send me shares of that one, whereas we will all send other shares of Y2 to the player 2. Right? Okay. So here is so that's and that's a sort of variant for a lot of cryptographic computation, including, for example, fully homomorphic encryption has a following similar sort of mentally similar structure. Instead of fully homomorphic encryption, it's an encryption that allows you to do this. Everybody encrypts their input, and there is some circuit, some computations that they want to perform on this input. But the computation can be done on ciphertext. So in public, given an encryption of X1 and encryption of X2, there is some procedure that creates an encryption of the sum or an encryption of the product. Or if it is a Boolean circuit, then encryption of an AND, an encryption of an OR, an encryption of NOT, etc. And if there is an encryption that allows us to do this, then we can compute also the computational encrypted data, get an encryption of the output, and then in the last phase, we just suggest somebody who has the decrypt must have the decryption key, but they only get this. So, like in a two-party scenario, if I have some data on a computer, you pick a key, you encrypt all your input under this key. It's a public encryption, so I also encrypt under that key. I process the computation, so I have the ciphertext. I give you the ciphertext. You are the only one with the decryption key you decrypt. It is actually fully homomorphic encryption solves a multi-party, at least two-party secret computation problem in a very beautiful non-interactive way. You just send me encryption, I do all the work, and I send you back the ciphertext you decrypt. Okay, so here's the easy part. The last gate is very easy. Look, if X is a value that is secret shared, so here's okay. Here's player 1, player 2, player N. Let's say that S is the secret sharing polynomial. And here is the secret that they are secret sharing. So the secret is x, which is f of 0. Actually, let's call this function fx. It's the secret sharing polynomial used to secret share value x. What are we computing? Class code. So here is x, which is secret shared. Here's y, which is secret shared. And we want to compute secret sharing of z, which is x plus y mod b. Okay. So let's say x was secret shared with polynomial fx. So what does this guy has? He has fx of 1. What does this guy has? Fx of 2, etc. And this guy has fx of n. Okay, what about y? Well, y is secret shared with some polynomial, let's call it f of y. The first guy has fy at 1, the second fy at 2, and the last fy at n. If they just added all the shares mod p, then this is a fx define fz of x to be define fz on okay, let's call it this input variable capital X to be defined as fx on this input variable plus fy on this input variable, and this addition is not p. So if this guy adds his two shares, he computes fz of 1. Because this is a polynomial, yes. So let's call this polynomial. This is a t-degree polynomial, and this is a t-degree polynomial. Yes. So if I add two polynomials, I get a t-degree polynomial. And by adding polynomials, I mean a function defined as the sum of the other two functions. Okay, so at every point, at every argument, I can define a function, which is this polynomial plus this polynomial, or computed on a function. And if you look, if this polynomial is a0x plus atx x to the t, right? So it's okay. This polynomial is defined by coefficients a0, a1. Okay, so this is a0 plus a1 capital F plus a2 x squared plus the dot, yeah. And this one is b0 plus b1 x plus b2 x squared plus the dot. Then what is this one? This one is a0 plus b0 plus a1 plus b1 x plus a2 plus b2 x squared. Yes, because the value of this thing at any point is this value, which is that, plus this value, which is that. So if capital X is a variable, then I group elements, and that's what I get, right? So this is first of all a t-degree polynomial. The second, you can compute the value of that. So let's call this C0, and let's call this C1, C2, dot, dot, dot. You can compute the value of this polynomial by locally adding the value of this and the value of that at point 1. And that value is the value of that polynomial at point 1. If the player 2 just adds his values of the two polynomials, so fx at point 2, think of this polynomial as a line, as a linear function. So D2, has a value of this fx line. And he also has the value of fy line. So he adds these two values. What does he get? He gets the value of this fz line, evaluated at point 2. Okay? And so if basically if each of them locally adds his share, which is his value, the two values of the two polynomials that he called, what he can compute locally is the value of this new polynomial, of this one. What is does this polynomial? I claim that the secret sharing polynomial does hold the correct. It's the secret sharing of the correct value. Because this is fz of 0, but fz is defined as fx at any point, right? Fz at any point is fx at that point plus fy at that point. So this is fx at that point plus fy of that point, which is x plus y. And all the computation here are multi. Okay? All arithmetics is done, this is the mod p. Right, and this is mod p, etc. What I'm saying simply is that two polynomials of t degree, if you define a new polynomial which is a sum of these, then sort of obviously it's still a t degree polynomial. And everybody can compute the value of that one by just adding the local values of the first and the second polynomial. And so without any computation really, the addition gate is trivial. Given secret sharings of x1 and x2, everybody can locally compute secret sharings of w1. The protocol for mult is not so. It's not like that. We need interaction. We don't know how to compute this in a non-interactive way. But it's not so horribly bad. There is it requires like a single round of computation. So there is something I can do, broadcast some information, and each of us does. And now we locally add all this information, and we have now secret sharing of the product. Instead of trying to show this product protocol, which is not so easy, I'll point you to some description of it. If you're curious, you can see it's a sort of a puzzle. If we have secret sharing of two polynomials, I mean, basically values of two polynomials, adding them is very easy. Everybody just adds locally. What about multiplying them? If x is secret shared with this fx polynomial and y is secret shared with fy, how do can we create a polynomial that is t degree and whose value of 0 is x times 1? Well, the start is not so hard. What if they just locally multiply their shares? What's wrong with that? That kind of works, and that's indeed the first step. If you define a new function that is a product, then indeed its value of this new function at whatever point, at let's say my index is I, is the value of this function at I times the value of this function at I. I do have both value of this function at I and this function at I, so I can locally multiply them, and I do get the value of this function at I. So am I done? Almost. If I define a new function as product of two polynomials, it works. The only problem is that the degree of the polynomial group. If this degree is t and this degree is t, then the degree of this guy is 2t. If I multiply, if you think of multiplying this expression and this expression, you get cross products, and the highest term is x to the t times x to the t, which is x to the 2t. So it's a 2t degree polynomial. It's good. It shares the correct value. The new polynomial does share the x times y. The only problem is that it's a degree group. Now that is a very common thing. Like that's actually the way you look at the fully homomorphic encryption. Again, addition gates are free. The arithmetic is such that you can for free add. The product makes ciphertexts possible, but the ciphertext grows. Here we have a similar thing, degree of the polynomial group. So the interaction is to convert a polynomial of 2t degree into somehow a polynomial of degree t. So we already have, by non-interactive multiplying of each of our values, values of 2t degree polynomials that share correct value. Can we reshare it somehow to reduce the degree of the polynomial? That's the whole thing. And then I will just leave you with this, that it can be done. It's not so hard, but I'll point you to some description of it. There's maybe one last thing that I would like to point out is that there is a sort of alternative class of there is an alternative class of constructions of multi-party computation. So first of all, there's computation from fully homomorphic encryption, but there is a class of computation that is that was done before that. And it's also non-interactive. So it allows one party to process data and give it to the other. The other does some grinding, and then sends the output, and the output can be computed by the receiver. So this thing, for every gate, we need interaction. Any multiplication gate. So the number of rounds and the communication complexity depends on the root gates of the system. The other scheme does not. If you instead basically don't have modulos, the inputs are just bits, and it's composed of XOR, basically composed of Boolean gates. Okay, so here is x1, x2, and there is a gate. Let's say, let's say an end, right, and then some other gate, let's say OR, right, and XOR, and here is, for example, NAND, right, and then I don't know, perhaps OR again. So it's a Boolean circuit instead of arithmetic circuits, and the inputs are bits. why can't we do secret sharing? Here's the subtle thing. We actually needed the degree to be somewhat large for this, because all the computation is mod P. So if this modulus is 2, even i's, the indexes are not, 1 is the same as 3. So it's like this third guy will get the same share as the first guy, right? So like nothing works. Like basically the modulus has to be at least as big, at least as big as the number of parties here for this secret sharing techniques to work. There is because I don't want to give you the whole thing, but there is a surprising technique due to Andrew Yao. It's called garble circuits. If the garble circuit technique is that for each key, this party picks 2 keys, K1 0 that represents the 0 bit, and K11 which represents the 1 bit. For this wire, he creates K2 0 and K2 1, etc. And for this wire, let's say that this wire has, this is wire 1, this is wire 2, etc. And let's say this is wire 5, and this is wire 6, and this is wire 7, and this is wire 8. Okay, so for wire 5, he also creates K50, K51, the random keys. This key, in some sense, will stand for encoding of the 0 bit on that wire. And this key will stand for encoding of the 1 bit. And it will be like so for all. Even the final wire, each of them will have 2 keys. And intuition is that if somebody gets, and then there will be translation tables that says, did you get this key? That meant computing 0. Or you got this key, that meant computing 1. So the final output will have a translation table. Now let's say this actually computation is only for 2. So this is a computation 2 from, this is computation 2 only for 2 people, for 2 parties, and for Boolean circuits. One party, let's say, all these bits are, all these inputs are from party P1, and let's say all these bits are from party P2. The party P2 will garble circuit F, meaning they will pick key pair for every wire. They will create encrypted tables for every wire that allows computing appropriate key of the output based on which of the 4 possibilities of inputs there were. So if there was a 0 bit on this, this means that this key was in play. And if there was a 1 bit on this wire, then this key was in play. If under this pair, this is an AND gate, so an AND of 0 and 1 is 0. Under this pair, you should encrypt this key. Because if somebody has this key and this key, this means that the bit on this wire was 0 and the bit on this wire was 1. So the bit on the output should be 0, and therefore they should get this. So here is an AND gate. Under K0 of the left wire and K0 on the right wire, I should output K0 of the, let's call it the input X and Y and the output Z. Under 0 of the X wire and 1 of the output wire, I should still encrypt 0 of the output bit. And under K1, KY0, I should also output 0. And the only key, keys under which I should encrypt K0, the output, this key, is KX1 and KY1. So in other words, garbled AND gate will include 4 ciphertexts, and encryption under KX0, KY0 of K01, all the way to encryption of under KX1 and KY1 of KZ1, right? So, and importantly, these are K0. So, the guy who creates the garbled circuit creates for every Boolean gate 4 ciphertexts. If there is a way to start it up, think of now for this guy's input, he knows whether on his wires the inputs are 0 or 1, so it's easy for him. He just sends the appropriate key to the other part. For these keys, it's not clear for these bits which key should he send. The left key, the 0-bit key, or the 1-bit key. There is a beautiful protocol called Oblivious Transfer, which solves that problem. Alice, the receiver, has a bit which says, I want left or right. The sender has 2 values, 2 keys. Alice gets only one of them, and only the one she asked for. Bob, the sender, doesn't know which one she got. You can do this with Diffie-Hellman encryption. It's like a super cute trick with Diffie-Hellman encryption that basically implements that surprising. Give me 2, and I'm not going to tell you. Give me 1, and I'm not going to tell you which one. And for sure, I only get 1. But you don't know which of the 2 I got. That's called Oblivious Transfer. So now Alice now has all the proper bits, all the keys that correspond to the proper bits for these wires. But she knows which bits these keys correspond to on her wires, but not on the other guy, because each key is like a random-ended string. So she doesn't know whether this key that she receives from Bob corresponds to the 0-bit or the 1-bit. And now for every gate, she looks at this encrypted, garbled version of the gate. She has 2 keys. She doesn't know which ones they are. She tries to decrypt this ciphertext, and let's say it's authenticated encryption, so she knows whether she decrypted something or not. Only one of these ciphertexts she will be able to decrypt, because for every, she only has one of these lines. She only has either this key, either this or that, not both. So only one of these ciphertexts she will be able to decrypt. And what does she get? The proper key on the output Y. Yes, because that's because the gate is garbled for the AND gate. Meaning that if your input was 0, on either you always get a 0. The only way you get a KC1, the output wire key that corresponds to bit 1, is if your input wire keys were both corresponding to bit 1. And you see, there's nothing special about it. For every gate, you can do this. Yes, because every gate is just some function between the input bits and the output bits. So you can, whatever the gate says, you just encrypt corresponding either 0-bit or 1-bit key in the proper row. Now, how does Alice not know that, well, she discovered, she decrypted this guy, right? So she knows, okay, the bits were 1, 1. It's easy. permute them. You don't send them in exactly this order. You take the 4 ciphertexts and you permute them randomly. And that's what you give to her. So she has to decrypt each 4, but this is a standard symmetric encryption where it has to be modified somehow so that like I have 2 keys instead of 1. But that's simple, just hash the 2 keys, and that's the key that you use to decrypt. So you see, non-interactively, she can take for each of these gates, what she gets is the little garbage table from the thing, which means 4 ciphertexts. These are standard ciphertexts. These are like AES, 4 short values for every gate. And I have 2 keys, and I try decrypting 4, and I get to 1. And non-interactively, I just take the next garbled gate and try decrypting, and one of them will succeed. Now I have the output wire on this, either K06 or K16. And I don't know which until I get to the end where there is a translation table that says, this key, if you got this key, that means a 0 bit. If you got this key, that means a 1 bit. And that, so I didn't tell you how Oblivious Transfer works. I'll send you to some description, which you'll see. It's like a beautiful, funky change of Diffie-Hellman. And this was non-interactive. Like they didn't need to compute. There's tons of questions like how to do this in a multi-party. Another question is actually combining the Tuesday stuff, zero knowledge proofs, with today's stuff. Because this was all assuming that everybody is a good person. Everybody does what they're supposed to. It's very easy to mess it up. Like the garbler could send also the nonsense here instead of correctly encrypted gates. You can, without loss of generality, you can use zero knowledge proof to prove that what you have done is correct without revealing anything. Likewise here. I can add 2 polynomials, but maybe I inject noise, maybe I change, maybe in the secret sharing, instead of giving you the proper share, I just gave you like a random value just so that to basically kick you out of the computation. But maybe there is a zero knowledge proof that I can prove to you, to everyone, that I have created these shares correctly without revealing them, right? Okay. I'll send you pointers to some papers so you can see, or even better, actually, presentations. That will be, so like you have it in some easier to swallow form. Okay, so thank you. Remember, there is a take-home exam. I set the date a little bit arbitrarily, so like I guess I can set it a few days ahead. There's only one constraint, is that we have to have time to grade it. So there is that there is a time that we have to file the grade. So that's, that's why I asked you to give it to me on Wednesday night. Thank you.